Alright, so to recap, last time we did like basically before actually working on the bot, like there's like 3 topics I'd like to review. So last time I did this one, dot product relation to projection, and that's like pretty important because everything else is based on that really. Then number 2, gradient significance, basically uses kind of like dot product and directional derivative to just explain why the gradient is the direction you want to go in to increase. It's just a natural thing to dot stuff against. Alright. Right. So this is assuming that like the prerequisites are obviously knowing partial derivatives. So let's say we have like just a function of 2 variables, f of x, y. So like we have say an x and a y, and then like there's like some like just some so like the function f is like the surface which is above which has some height to it. So like if we take some x and some y like right here, and we kind of raise it up, so like for this given x and this given y, we get this point on our surface. Now the question is like the gradient basically is so it's basically this vector, the partial derivative with respect to x, the partial derivative with respect to y, and then we can kind of specify that that's at the point xy. So like what is df dx? Like what does that mean? Well, if we just kind of take this y right here and we just kind of pin it to this value, right? Like we just kind of like for a fixed value of y, like we can see that the surface kind of like we are basically holding, like we're kind of creating, like we're kind of like chopping a slice vertically. Like we're just inserting a plane, which is kind of like that. Like we're just kind of bringing this plane down to like kind of give you a trace. Like this is kind of the path. Like if we're at this point and we only increase or decrease x, we just go along, like we just kind of go along this line right here. Then we then our surface follows this path. So right here, we're like kind of, if we step a bit forward in the x direction, like just a little bit here, then what happens is we drop. So like this change in height from here to here is our df, and that's our dx. And then as we take a super small step size, like we converge, like basically like this is like the limit, like the limit as h approaches 0. I mean, well, there's no need to write it out, like it makes sense to me at least. So basically, like df dx is like you take a very tiny step here and then you kind of drop a little bit, and then df dy is the kind of the same thing, except instead of like this plane right here, we kind of like bring forth another plane. Look, it's getting too cluttered. Let me just delete everything. So if we take a small step here in the x direction, we get some change, like right there maybe. And then if we kind of step forward in the y direction, right here, then like holding x constant, we have kind of like a curve here. We go, say, up a little bit. So then the question is like we know if we kind of step in the if we step in like the 1, 0 direction, like x and y, then what we get is we get like df dx. And if we step in the 0, 1 direction, we got df dy. Now the question is like, how do we generalize this? Let's say we step in a comma b, and for good measure, let's pretend that this is a normal vector, like 0, 1, 1, 0, like a squared plus b squared equals 1. Then the question is like, what is df d let's call this v equals ab, right? So like one kind of idea is like the tangent plane approximation, which is how I think of it personally. Like we have like this point here, and if we move in the x direction, let's say that if we kind of move in the x direction, dx, we get some change in height. Let's call this dfx. Like the change in f due to x. And now let's say like if we kind of go in the y direction, like a little bit of a dy step, then let's say that like that gives us a huge change. Like from here, let's say that from this point we kind of really kind of skyrocket, like we go all the way up here. Now let's say that like v is like equal to like 1, 1, that is, it's kind of like blending, but oh wait, no, it's a normal vector, so like 1 plus 1, it's 1 over square root of 2, 1 over square root of 2, because a squared plus b squared equals c squared, so like, yeah. Then the question's like, if we go here, and then we go here, if we do dx, then we do dy, like what will it be? Like this change in height, let's call that delta of y. Then kind of, the idea is that you can kind of look at it in terms of like go x first, and then from here you can kind of like step y, like you kind of travel here for the x, then you travel there the y, and then the difference between here and here is the sum of those two. So like here you were like in the point on the plane, like on some point in the surface, we take a step in the x direction, and as a result we kind of move here, and we take a step in the y direction, we move there. Alternatively, we could kind of take a step in the y first, and then take a step in the x, and like we'd kind of still get here. So it's like this line right here, and this line right here, which are kind of vectors kind of given by these two. It's kind of like a point and slope idea where that's the point and these are both the slopes in like these directions. Then we can kind of use these two to basically create like a plane. Like this whole thing kind of stretches this way, that way, like it's basically like it creates an entire plane. So like at this point right here, this plane kind of is an approximation of like the actual surface. Like if your point here, it's like we kind of like look at the change in x, look at the change in y, and then like the whole thing basically kind of gives us a plane that at this point like generally approximates values in our local neighborhood. And like as we go super zoom in, like we really zoom in, like we like take the point and we kind of like blow it up and like look in, they kind of are pretty approximate, like they're really close to each other. Now like so basically like the kind of idea is that like df dy equals df dx times a, because like we took one step here, or well, we took a tiny step here and a tiny step here, but like basically like yeah. So like where this kind of tangent plane intuition kind of explains it to me, like if we take like if you have a and b, right, and then like we take a steps in the like that's the x coordinate and that's the y coordinate, like right here. So like we take a steps in the this x component. So like we get, well, I shouldn't say a steps because we're actually kind of like making this vector a b, we're kind of like converging, like we're kind of making it an infinitesimal, like a super tiny amount. But yeah, let's just pretend that like we kind of get a steps in this direction, so like we get this much contribution to the change, and then we take b steps in the y direction and we get that much contribution. So like in total, like that's the sum of it, like this. And then the idea is that when we kind of limit it, like we kind of zoom in a lot, then this thing holds, and this will be the directional derivative, which we can also express, like, if you go back to the notes, the dot product relation to the projection. We can also rewrite this as the gradient dot v, because v is just AB. So that's kind of like, we could actually stop here, like the gradient dot v. So like the gradient significance then like is like a natural question arises, like where what's like right now, like if we is like 1 over square root of 2 squared, if we kind of like go at a 45-degree angle, then we basically kind of get this much change. Now the question is like, what's the best angle to choose? But like, if you think of it in terms of projection, like any v is basically being projected onto the gradient, then the direction that gives us the most like bang for our buck is this direction itself. Like, if this is our gradient, and that's some v, and the dot product is the projection, then the best v to choose is just like the gradient itself. So like that's kind of like a good, like that's decent intuition, at least for me. Now like I mentioned the chain rule, and like I think that's like kind of, I mean, I briefly looked at, like before doing this, like yesterday I just like kind of skimmed my math book, and like here's kind of the way that they do it. Like we have f of x, y, and then like there's like this trick which like they introduce g of t, right? So like it's parametrization. Like they're basically introducing a t parameter, where like the kind of idea is like right now, like if you just look at like df dx and df dy, right? Like we basically can like kind of look at the x-axis and we look at the y-axis, and like if we kind of hold y constant and we just only operate on the x-axis at this point, we kind of like get a slice, right? In kind of same way, if you're at this point here and like we kind of only change y but we hold x constant, that means like we kind of travel from this point on the xy plane, like we only go in the y direction, we get some change, only go in the x direction, we get some change. And now like by kind of introducing like AB, like a generic vector, then like, and we're going in like the 1-1 approach, or like the kind of an angle, then it's like we have an x-axis, we have a y-axis. Like, can we not just like introduce another number line right here, and like we can call that t? So like if this is like our initial point, then like given some t, like how much change in f do we get? Well, like how much, because f is a function of x and y, right? But x and y, like if you kind of move t here, like it's some, like we take, the idea is like how do Miro's being updated. Anyways, okay, reconnecting. Right now I cannot edit it because something is going on. Let me duplicate it. I don't want to click refresh and lose everything here. I hope I didn't lose everything. Nope, not going to give an email address. Okay, that's good. So anyways, basically like we kind of create, like we kind of look at x and y in terms of t. Like we basically have x equals to a times t, and then y equals to b times t. Actually, let's just call this point like, let's call this point right here x naught, y naught, y naught. So like this gradient, like here, let's actually like kind of specify that it's the gradient at x naught, y naught, and like dx at x naught. Let's go vertical sign x naught. I think that's the notation. And df dy at y naught. I'm not sure if like the notation's like commonly used or if that's even a thing, but basically I'm just kind of specifying makes the gradient df dx at this point x naught, y naught, and this is df dy at the point x naught, y naught. So the question is like, how do we find this, right? Like, if we're like, how do we find, like, what we want to do is we want to like derive this, like at least how the way my math book derived it. So anyway, so the idea basically is like, so we have x equals at, so like when t equals 0, oh yeah, plus, yeah, that's why I introduced these knots, plus x naught plus y naught. So basically what we want to do is we want to like solve g prime of 0. And this right here, g prime of 0, is going to be our is going to be df dv. dv at x naught, y naught. So like back to this picture right here. So like this is x naught, y naught right here. That's the point. And then like if you kind of go back to the xy plane, like if we kind of move in the x direction, we get some change. Move in the y direction, we get some change. And now like we basically kind of introduced a new kind of vector, and that vector is v. And it can be kind of like so like v is basically like a and b, and we can kind of like, rather than just kind of like have a number line for like a line, like a number line for x, a number line for y, we basically kind of like introduce a number line for t, right? So then like basically like what this df dv at this thing, like what this basically means is like we take a very tiny step in this direction and we get some change here, right? So like that change in terms of taking a step in this direction t is basically like g prime of like t, where t equals 0, and that is exactly what we want here, the directional derivative. We take a tiny, like we take a little step in this v direction, and then what we get is that affects some change in f, and that is g prime of 0. Now, so we want, like that's what we want. So how do we solve this? Like that's where like I added like this last thing here, chain rule. So basically like, what is dg dt, right? Well, the derivative of g with respect to g, we basically kind of use the chain rule as like, so g of t, I didn't even define it, I'm so stupid. G of t equals f of x of t, comma y of t. So basically, like, first we close this parentheses inner, then we close outer. So like, again, like this point here, x naught, y naught in the xy plane, we can kind of step in x, we can step in y, and now we can step in like what kind of knobs do we have? In this axis, our knob, which we can rotate, is like the x knob, then the y knob. And then to go in this v direction, which is like kind of a composition of x and y, we can kind of express this composition of x and y, like how they both contribute to we in terms of like a and b. It's starting to sound like linear algebra, like the x component, the y component, like it's just a and b. So like this is kind of the parametrization. This is how we like define. This is another way of writing like this line out right here. So anyways, basically, so like we just like rather than f of just being x and y, we basically want to write f as a function of t. Now we can't use f because the name f's taken, so like a, b, c, d, e, f, g. So like we introduce g of t as f of x of t, y of t, right? So then like, so like basically like now because like df dx, df dy is like we have a single like the partial is like a single change in x, like holds y constant, like we only change in this direction. How much change do we affect? Whereas now like g of t basically kind of generalizes it, whereas not just the x direction but the y direction, but any t using like these two like this parametrization will kind of give us the change in f, like will basically give us the change by a little step of t. So like we want to solve dg dt, and not just like that's like a dg dt is like kind of a function of t, but more specifically we want it at 0 because at t equals 0, the point which we are at is just x naught, y naught. So like here's where the this chain rule comes in, right? So like dg dt is basically like kind of, it's like g kind of, because f has x and y, so like it's like df dx and df dy, but like df dx and df dy in turn change t. Specifically, we can kind of look at these two terms, right? It's kind of dg dx times, this is like the chain rule in multiple dimensions, more generalized chain rule, plus dg dy. So the left term kind of gives us like how much we get from it kind of like gives us like this thing right here, how much we get from the x direction in this vector, and that's kind of the y direction component. The dy dt, like I look at the chain rule and kind of like imagine that we cancel this and that we cancel that, and like we just, that's kind of like the way I view it, like a shorthand. But anyways, so like, but we know dx dt, like if we just differentiate x with respect to t, this just becomes like this basically becomes, let me take from above. So this whole term right here is simply a, and like this dy like this term is a, and then this term right here is just it's just b, because like if you like dy dt is clearly b. So then dg dt at like at 0, right? At the point 0. So like if we kind of like do this and do that at this point x naught, y naught, because like t equals 0 gives us that initial thing, then we got df dy equals to this, like at the point 0. I mean, at the point t equals 0, we get our initial x naught, y naught, and the directional derivative is indeed dg dx at the point x naught, y naught plus dg dy at the point x naught, y naught. And here we go, like that's the directional derivative, and that's, so we basically express the directional derivative as a dot product of the gradient dot this vector here, which in other words explains why like that kind of like is a significance of the gradient. At least it's a nice significance. it's like the direction we want to step in to like affect the maximum change, because like that change kind of comes from the x direction and the y direction, and like you can just add them up. Like when I initially learned this, I thought that like that did not make sense to me, because like how can we just add these two changes up, right? Because like what about cross terms? Like what if like if we go in the x direction we get something, y direction we get something, but then if we do them both, then what if like there's like some cross term where like I don't know. I just thought that like adding them up seemed like it was missing something. But anyways, I mean that's just I guess hyper local to that point. Like that's just how it works. And like this kind of reminds me of like the math I was doing last time too, when I was kind of like, I think I still have that board. Like, right, yeah, I do. It's gonna like 1 minute left to save your board. Well, I'm not gonna sign up. I don't sign up for these things. Like right here, when I was talking about like a dot b, right, and like looking at the ith term, actually, like, right after I finished it, I kind of like realized I kind of wanted to explain something else. Like when I was introducing like these u of i's, like I was taking like the r, like I had a space of like, oh, this shouldn't be ri, there should be r of k actually. So yeah, so like basically like what one thing I wanted to add from last time actually, because like this whole sum of contributions of like the bi, like the ith entry in b, kind of how it like what contribution its projection onto a, and we just sum them all, kind of reminds me a lot like how the it just kind of reminds me a lot of like how we just kind of sum the x contribution, the y contribution, like the a and the b, like because those are x and y coordinates. That kind of reminded me of like this dot product thing where like each of these is like kind of the in the ith dimension, the projection of b onto a in the ith dimension, right? So like one way to write like if like b, like if we have like so like in the like let's just say we have like a ijk, like we have an x-axis, a y-axis, and a z-axis, exactly like we were taught. Like z is just f, right? Then like the basis vectors, like x could be like 1 0 0, and then y is just like 0 1 0. That's our typical standard basis, and then z is just 0 0 1. And oftentimes like we kind of call this like I hat, Hij, so then y would be j hat, and then z would equal I hat, j hat, and then k hat, right? So like this could kind of be like 1 0 0, or also known as I hat. Let's just get rid of the sign. It's kind of like, yeah, this is just I hat. And like a basis is like, this is the identity matrix, j hat. Kind of annoying, I have to put a dot and then a hat on top of the dot, like just anyways. And like this is like, and this is this whole column right here is k hat. That sounds like k hat, but anyways. What if you have s hat? anyways, anyways, I digress. So like when you think of bi, right? Like bi has like, let's just say like we're dealing in 3 dimensions, like k equals 3. Then what b basically is, like if b is like b1, b2, and b3. Like, I know I mentioned the word coordinates and like scales down and squishes, but like just to make it kind of explicit, we can basically like say b, like b has these coordinates, but like what does that actually mean, like geometric? Like what is, like we can kind of expand this out. This is like very, very basic linear algebra, maybe in multivariable calculus, like bi, where I is this 1 0 0 plus bj, sorry, b2j plus b3k hat, right? Sorry, I'm still thinking about. Anyway, so basically, like the idea is like kind of like it's kind of like linear transformations. Like if you apply like A transpose to B, like what you're ending up doing is like you kind of like take both sides of this whole thing, and you just kind of A transpose that, right? So like the whole idea is kind of like we basically kind of like what we're basically kind of doing here is like we're kind of like thinking of it like we're splitting B up into like it's an individual like kind of directions, like how much it stretches in these three directions. It's very like orthonormal bases, like you can Graham-Schmidt. I mean, it's just so like fundamental. I mean they're super useful. Like very kind of easy to visualize as like a simple coordinate, everything is 90 degrees to each other. Yeah. But anyway, so like basically like we kind of took this equation and then we kind of like AT, like dot product on the left from both sides. So like A dot B, right? The projection of B onto A. Like it is the projection when like both A and B are unit vectors, which we're just gonna assume for simplicity, right? So like that's just like AT of like this is sorry. Like B1, like these are actually scalars, so like we can like push them out, right? So like B1 of A transpose of I plus B2, because again, we can just push them out. A transpose of J hat. I kind of want to just ignore the hats, but I already started them. Plus B3 times like A transpose of K hat, right? So like this dot product is kind of like the like three different sums. Like kind of like if you look at this this image, okay, I have lots of stuff. Like I have too many images. Yeah, so like right here, like we have like B projected onto A, right? And like this like B projected onto A gives you this entire thing right here, right? Now, if we kind of express B in terms of like B1 plus B2, then the projection of B onto A, its length, this much, can also be written as like the projection of B1 onto A and its length, plus the projection onto B2 of A, its length. So like this length plus this length equals this length. And like that's kind of like the idea being done. Wow, so much to scroll down to. Like kind of here, like we kind of like B is kind of like we like B is a bunch of like sorry, B is a bunch of coordinates B1 dot 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 BI all the way to BK, and like each of these coordinates like has their projection like each of these coordinates. So like each of the coordinates are coordinates that like the ith coordinate here kind of references the ith. Okay, that's kind of like the word like in this case like the ith in these listed bases. So like that would be like u1. I'm just calling u for unit vectors like u2 and like u3. So like u of I, like if you have some u of I, then like you'd have like b of I times that. So like this is the just some ith dimension, and the contribution of ith dimension to the dot product, like how like when we do like ai times bi, the contribution of bi project onto a, like like so like basically like we're kind of like taking all of these contributions of all the bi, like all this like bi is just a scale of ui, which is just a unit vector in the ith dimension. And then like if you look at that projection, its projection, ui's projection onto a, right? And like we get some contribution from that dimension, and then the whole idea is we just kind of like sum everything up, which is quite reminiscent of like the chain rule, like this thing right here, where we just kind of like sum up all the kind of like a dimension, like the x dimension and the y dimension, kind of like sum those two up, kind of like right here too. We're just kind of like looking at the ith dimension, jth dimension, kth dimension, just all these like different dimensions, and like we kind of look at how like this dimension like going like let's say in the jth dimension like which is y like kind of like b's like y coordinate here, like how that like plays into projecting onto a, and then we just sum them all up. As a recap, like how do you actually contribute, let's say like b2, or like how do we actually contribute like its like what is its projection onto a, right? Well, b2 is a scalar, so it's just what is like b2, like what is this term? So b2 is a scalar. We can actually set this aside. Like that's where like the scales down and squishes or squeezes is like the term I mentioned last time. So like we just kind of like, to get this term, what we really need to do is just get this term and multiply it, like scale it down by b2. So what is at of j? Like how does a, like what's the projection of a, like what is the this j hat, like what is this ith dimension, like how does that j hat project onto a? And that's where the symmetry thing comes in, like from the beginning, like which I saw in actually that 3b1, like this this YouTube video right there, like that's kind of like a really kind of like, that's kind of where that comes in, where if you have like a and like that's your y, that could be your x, whatever, then the projection of this y onto a, like this length right here, is the same as the projection of the length, like the length of the projection of y onto a, which we want, because like this length, the projection of j onto a is the same, the length of that is the same as the projection of a onto y, right? So like that's kind of like this duality, like the symmetry about this axis right here. Alternatively, you can look at it as like two different right triangles, this right triangle and that right triangle, and both these triangles have like this common angle, and they also have a hypotenuse of 1 because a and y are both unit, a and j hat, like that's j hat, are both unit vectors. So basically like there's kind of like a duality, like projecting this onto this and that, and just like, again, dot product's commutative, right? Like a dot b is the same thing as b dot a, but this whole time I'm kind of viewing it as actually like matrix, like I'm like kind of viewing this as the projector. You're projecting this and the projectee, like you're projecting this onto this. I was kind of like assuming that, but like these are both like kind of, you can flip-flop the orders, but so it's like j hat onto a is kind of like, you can kind of flip it and like view at. So like what is a transpose dot j, right? Like what is that? Well, if you look at the definition, like 0, 1, 0, basically like we just zero out everything else and we're left with just 1. So like at dot this, or like in more generally, at dot u of i hat, right? Like u of I, where u of I is like, that's u1, u2, u3, just u of I, like at of that, right? Well, this thing, you just zero everything out and you're just left with the ith coordinate, which is ai. So in the general case, we just kind of like take ai and we scale it down by bi. So you just do ai times bi, and we sum off them over all the i's, and then that is the definition of the dot product. So yeah, that's pretty neat. Also, like, I mean, at dot j, right? Like, again, like you can kind of like look at this kind of definition right here, right? Like, it's basically like just how like the coordinates of a vector, like basically like any vector like has a bunch of entries, and those entries are like, those are the projections of it on the, like if you have just like some vector, like just super basic, like just v1, v2, just say just like these entries of any vector are like how far along the specific dimension, like how far along the coordinate axes you have to go to. Like this relationship right here, like for b, like expanding b in terms of this, you can basically do that for ai too, for a. So like just how we wrote like b is b1 I hat plus b2 j hat plus b3 k hat, you can also do a equals a1 I hat plus a2 j hat plus a3 k hat. So like, and like with this, like, so like if, so like the, by expanding a vector in terms of like, looking at in terms of like, kind of like, if you have like some vector here in 3D space as like, okay, that's not it, but like, that's your origin. You have like some vector here, like, you kind of go here in the x, and you go here in the y. So like you have an xy plane, you kind of like dot 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 dot, you go x steps, you go y steps, and then you kind of go z steps here. And this point is the vector like x, y, z. Then the projection of this vector onto the x-axis is simply x, right? It's this. If you kind of like drop a perpendicular, and then like if you kind of take this thing and you kind of like drop a perpendicular onto x, like that would just give you x. And then its projection onto the y-axis right here is simply y, and the projection of this vector onto the z-axis is simply z. Like we basically like if you have v equals to x times I hat, right, plus y times j hat, plus z times k hat, then one question is like, what is the projection of v onto the x-axis, right? Like, so like to do that, the projection of v onto the x-axis, right? Let's call this like let's call this like p of x, and we can basically kind of apply this p of x projecting onto x operation to both sides. So like basically like p of x applied to this term right here, to the like p of x onto this term will simply isolate out this x right here. That should be kind of, I mean, this should be kind of self-evident. Like the projection of x of, like, if we take like I, the unit vector, and then we kind of like, because like, and we kind of like take x steps, then we land here, right? So like, when we like, well, by px, we'll define that as like, we project it onto the x-axis and take its length. So like, and that's basically what dotting it, like we're basically doing we're doing a lot like kind of like the whole dot product stuff. But anyways, we're like p of x we're defining as p of x applied to some vector is we take that vector, we project it onto the infinite x-axis, and we take its length. So like it's a linear operation, so like we can kind of apply to both sides. So then if we do p of y on this term right here, well, it's already on the x-axis. So like x of I is the projection vector, like the projected vector, and its length is just simply x because that's unit vector. Now, the key thing is these both, when we apply p of x onto these both, they're all orthogonal. They're all like 90 degrees to this axis. So like its projection is necessarily going to be 0. So everything just zeroes out and we're left with that. And that's basically why, like going back here, A transpose of J, or more specific, more generally, A transpose of UI, again, the ith base standard basis vector, is simply A of I. And then we're scaling everything down by B of I, and then that's kind of how we get this whole AI.bi business, and we sum them over I. And then what do you know? That ends up being the definition of the dot product. We basically do this, and that's like the definition of dot product. So I think that's a good point to stop, at least for now. So like we've basically covered this, and then we've kind of went back to this, and I just kind of added a bit more and kind of talked about this whole linear algebra notion of like kind of summing contributions, like x and y are orthogonal. So like we're just kind of like summing up orthogonal component contributions. And then I guess next time I'll discuss projection matrices. And then I'd like to finish on the note that like this technique which I just did at the very end, like where like I took an equation, like I took like x equals to like the sum of like something like, or like z equals to like abc. I've done this like at least twice. I know I've done this a few times, like kind of like took the whole thing and like done like some like projection, or like some, like I did projection on both sides, or I did kind of like a transpose on both sides. Then like a neat trick is that like by doing that, and like if these are all kind of orthogonal to like if you have like a hat plus b hat plus c hat, and like everything is mutually orthogonal to each other, then like it's quite possible that like we can zero things out, and we will definitely see this technique being used in projection matrices. So yeah.